when you are working with ARM Cortex-M processor, the T-bit should always be 1. The LSB, that is bit 0 of the program counter, is linked to this T-bit. When you load a value or an address into PC, the bit 0 of that value is loaded into the T-bit. Hence, any address you place in PC must have its 0th bit as 1. This is usually taken care by the compiler, and programmers need not to worry most of the time. Don't worry about these rules. Most of the time, it will be taken care by the compiler when you code with high-level language such as C. You should be careful only when you are placing some raw value or raw address into the program counter. And you should make sure that that raw value should be odd. That means the 0th bit of that address should be 1. For example, let's say you are dealing with some function pointers and you are initializing a function pointer with a raw address. Then make sure that that raw address is odd. Or you should be careful whenever you are dealing with inline assembly codes using the program counter. But if you are using pure C programming, then you need not to worry about all these things. The compiler will take care of it. This is the reason why you see all vector addresses are incremented by 1 in the vector table. So if you just take a look into the vector table, all the addresses are odd, isn't it? The reason is T-bit. Let me demonstrate the effect of T-bit using a small exercise. Here I have a project T-bit and I have a main.c. Let me pull some code from my previous project. Go to this project access levels and let me just use this code. Here in the main function, what I'm going to do is I'm going to create one function pointer. Let's say void function ptr. This is a function pointer variable. And let me initialize this variable with the address of, let's say, this function. Or you can just write like this. Let me remove this. Remove this as well. I just initialized the function pointer with the address of this function. After that, I will call that function underscore ptr. You have to use the parenthesis and semicolon to dereference that function pointer and jump to that function. Here, at this point, what exactly happens? At this point, the address of this function is loaded into the program counter. That's how program counter jumps to that function. Let's see that. Let me execute this. Here, just observe the variables tab. And here you can see that the value of this function pointer is this one. This is the address of this function. And observe this value. This value is odd, isn't it? 0th bit is 1. That's what compiler did for you. Before storing the address of this function into the function pointer, the compiler made the 0th bit as 1 of this function's address. The true address of this function is even, not odd. You can check that. Let's do one thing. Go to the editing mode and right click on the project. Go to the project folder. Go to debug. Open T-bit list And here, just search for that function. Here it is. You can see that the starting address of this function is E1. This is 1E8. But what you are seeing here is 1E9. Who did that change? That change is done by the compiler. So the compiler takes care of that. At this step, what you are going to do, you are going to dereference the function pointer. What does that mean? That means you are going to load the value of the function pointer into the program counter. That's how program counter jumps to that function. When that happens, 0th bit of this function address will be copied to the T bit. That's the reason the function address 0th bit has to be maintained at 1. Otherwise, T bit will become 0 and that will cause the exception. If you observe the disassembly, you can see that here we are going to use the BLX instruction, that is branch indirect. That is, the value of R3 will be copied into PC. That's what BLX does. Let me enable the instruction debugging and just do single stepping and check the value of R3. R3 is 1E9. This value is now going to be copied into PC, and that value has to be odd. If you do single step, you can see that control reaches to this function, no problem. Let's do one more change. Instead of this, let's hard code the address. I'm going to take the raw address of this function and I'm going to hard code that. And let's just typecast this into void stop. Now let's reload this project. Let's do step over, and here you can see that activate this single stepping. If you just check R3 here, R3 is even address, and that we are going to place in PC. In that process, the 0th bit of the address is going to be copied into the T bit, and T bit will become 0. That will cause the exception. You can see that. I'm going to single step. So here it is. I am in a hard fault handler because that triggered the fault exception. And if you go to the fault analyzer, you can see that hard fault detected. And the reason is attempt to switch to invalid state. So you'll learn more about all these fault exceptions, maybe in later sections. But not maintaining T bit as 1 will cause this exception, that is attempt to switch to invalid state. That will be escalated as hard fault exception. That's all about T-bit and the importance of T-bit. I'll see you in the next lecture. In this section, let's learn about memory map and bus interfaces of the ARM Cortex-MX processor. First, let's understand what exactly is a memory map of the processor. Memory map explains mapping of different peripheral registers and memories in the processor addressable memory location range. The processor addressable memory location range depends upon the size of the address bus. The mapping of different regions in the addressable memory location range is also called as a memory map. Let's understand this with this diagram. You have a processor, let's say ARM Cortex M4 processor. This is an interconnect. This is a bus which connects processor to the various peripherals of the microcontroller. The peripheral could be the GPIOs, it could be timers, ADC, I2C. There are various peripherals on the microcontroller. The processor also communicates with the memory. There are mainly two types of memories: code memory and data memory. Code memory is the place where you keep instructions of the program, and the data memory is where you store temporary data of the program. Let's say ADC has some data and it wants processor to fetch that data and store it into the data memory, let's say. How do you think the processor communicates to the ADC? Of course, it communicates with the ADC through some bus interfaces. That means there is a bus which connects processor to various memories and the peripherals, and that bus, we call it as a system bus. The system bus has 32-bit address channel and 32-bit data channel, or you can call it as 32-bit address bus and 32-bit data bus. Let's say ADC peripheral has some data, and that data is stored in one of the register of the ADC, and now it needs to be stored in the data memory. How do you think processor is going to access that register? What processor does is it produces that register's address on the address bus. And when that address matches with the address of that register, the register will be unlocked and the value or the data of that register will be released onto the data bus. After that, that data reaches to one of the internal register of the processor. And after that, processor stores that data from internal register into the memory. That's how the processor communicates with the peripherals and to the memory. Basically, you should be using two instructions here. One is load, that is load from ADC into the internal register of the processor. And after that, you would use the instruction store, which stores the value of the register back to the memory. On the ARM Cortex-MX processor, this bus interface is of 32-bit data channel and 32-bit address channel. That's the reason processor can produce 4 gig different memory location values. So from 0 to FFFFFFF. That's the processor addressable memory range. And in that range, different regions are fixed by the processor design. This is a fixed one. You can't change it. So this is fixed by the processor designers. And that's what we call as a memory map. For example, when the processor produces the address 0, that means processor wants to talk to the code memory. That's the meaning of that. You should not design a microcontroller in such a way that your peripheral register addresses fall under this region. ARM says in this region, you should only keep code memory. A code memory could be anything. It could be embedded flash, it could be WPROM, it could be ROM, or it could be OTP, anything which can host the code or instructions of the program. In this memory region, the microcontroller vendor should connect the RAM. This region is for RAM. And the microcontroller vendor has to place all the peripheral registers in this region. It should start with 0 cross 4 0 0 0 0 0 0 0. If you have any external RAM such as SDRAM, and that would fall in this region. That means when the processor produces this address, it would be talking to the external RAM. It will not be talking to these peripherals or these memories. Like that. That's a mapping of different regions in a processor addressable memory location range. That's what we call as a memory map. Let's understand these regions one by one. Let's start with code region. Code region of 512 MB. That means maximum you can connect 512 MB of code memory. That's huge, isn't it? Usually microcontroller vendors give internal code memory of 1 KB to 1 MB or 2 MB. That's maximum actually. They usually don't give internal flash of 512 MB. No, they don't give such huge memory. If you need more memory, then you can always go for external memory. Like you can connect an external NAND flash, or you can connect an external NOR flash, something like that. This is the memory region where the MCU vendors should connect the code memory. Different type of core memories are available, like embedded flash, ROM, OTP, WPROM, etc. Processor by default fetches vector table information from this region right after the reset. So that's a default behavior actually of the processors. But in the microcontroller, you can change that by using boot pins of the microcontroller. Let's move to the next region, that is SRAM region. The SRAM region is in the next 512 MB of memory space after the code region. It comes right after the code region in the memory map. So this is mainly used for connecting SRAM, mostly on-chip SRAM. SRAM is a data memory where we keep our temporary data, something like that. And the first 1 MB of the SRAM region is bit addressable. I'll talk more about bit addressable memory regions later. That's what we call as bit banding. And you can also execute program code from this region. You can also keep instructions here and you can execute. Next region is peripheral region. The peripheral memory region also has the size of 512 MB, used mostly for on-chip peripherals. On-chip peripherals of the microcontroller. Remember that. The processor peripheral registers will not fall under this category. For example, NVIC, that is Nested Vector Interrupt Controller, is a peripheral of the processor. Its register will not fall under this region. This is dedicatedly for microcontroller or vendor-specific peripherals, such as RTC, ADC, timers, etc. Like SRAM region, the first 1 MB of the peripheral region is also bit addressable. And this is an execute never region. That means you cannot execute code from this region. Trying to do that will result in fault exception. Basically, this is to prevent the code injection attacks. Like someone can transmit a code through the peripheral and he can make processor to execute that code. To prevent that attacks, usually peripheral region is execute never regions. Next is external RAM. Suppose if you need more RAM for your project, for example, let's say you are using some graphics related project, or if you want to create some frame buffers, or if you want to keep some video information or audio information, something like that. In that case, you need more RAM. So in that case, you can go for external RAM connection. You should connect the external RAM in this region. Your external RAM registers will fall under this memory region of the memory map. External device region. This is a region intended for external devices or shared memories. This is also execute never region. You cannot execute code from here. Now comes private peripheral bus region. This is a place where you see processor peripheral registers like NVIC registers, SysTick timer registers, and various other control related registers of the processor. They all fall under this memory region in the memory map, and this is also execute never region. In the next lecture, let me talk about bus protocols and bus interfaces. I will see you in the next lecture. In this lecture, let's understand about bus protocols and bus interfaces. In Cortex-MX processors, the bus interfaces are based on a specification called Advanced Microcontroller Bus Architecture, AMBA. That's a specification which is designed by ARM, which governs standard for on-chip communication inside the system on chip. So a microcontroller vendor who designs a microcontroller based on ARM Cortex-MX processor. So the on-chip communication, that is the communication between a processor